Welcome, everybody. Thanks, Tommaso, for accepting our invitation to talk here at the CosmoVerse series of seminars. Tommaso is Professor and Vice Chair of Astronomy and Astrophysics in the Department of Physics and Astronomy at UCLA. Prior to his current appointment, he was a Professor of Physics at UC Santa Barbara, a Hubble Fellow at UCLA, and a postdoctoral scholar at Caltech. He holds a PhD in Physics from the Scuola Normale Superiore in Italy. His research interests include fundamental physics and cosmology, galaxy formation and evolution, and supermassive black holes. Today, he will present the Hubble constant from gravitational time delays. Tommaso, you can start, please, when you're ready.
Thank you so much, Eleonora, for inviting me. I have to say I'm especially pleased to give a talk on February 29. This is not something that one can do every year. So I'll take this opportunity, and thanks for those who are attending. So there's a lot going on in gravitational time delays, and I want to give you some history and some updates. Of course, this is an important part of the current debate about the Hubble constant, the so-called Hubble tension. So let's get started without further ado. So I'll give a brief introduction to Hubble tension and its meaning. Of course, this audience doesn't need much in the way of an introduction, so that would be very brief. And then I want to walk you through the steps of time delay cosmography. How does it work? A brief history. How do we do it now, and why do we do it blind? Some research results and the current focus on systematics. And then I want to show you our multi-pronged approach to reach better than 2% precision and accuracy in a number of different ways. We have a number of programs that will get the precision to between 1 and 2% in a hopefully short time. So this is the story in a nutshell, the expansion history of the universe. We know that the universe is expanding, and there are different phases. The most recent one is acceleration due to dark energy. Prior to that, there was deceleration from dark matter. And the current expansion rate of the universe, the so-called Hubble tension, Hubble constant, can be measured in a number of ways. In the local universe, the so-called late universe probes, we just measure directly the current expansion rate, like the Hubble's law. But it can also be measured from early universe probes in a way that is a little bit indirect. So people measure some quantity in the early universe and then extrapolate to the present day based on some cosmological model. And then the extrapolation yields the current expansion rate of the universe. And the big surprise of the past 10 years or so is that there's been a divergence between early universe probes and late universe probes. So in this now dated figure by Wendy Friedman, it's shown the cosmic microwave background inferred, Hubble constant in red, and the one determined from the local universe. And as error bars have shrunk over time, there's been a growing tension between the two forms of measurement. A most recent version of this tension is shown in this very complicated plot. You don't need to read all the labels here. Suffices to say that the ones on the top are early universe probes, and the ones in the bottom are late universe probes. And the purple and orange lines, or shaded areas, represent some sort of mean of those two classes of models. And you can see that there's a very compelling tension between the two. Most of the direct local probes seems to prefer a larger value of the Hubble constant, something of the order of 73 or 72 kilometers per second per megaparsec. And early universe probes tend to cluster around 67 or 68 kilometers per second per megaparsec. Of course, this is growing in tension, and the solution of this tension is not easy. So there's been a number of papers, and I'll just show 3 here, that show how difficult it is to reconcile that. So one solution is possibly increase the expansion rate just before recombination to change the sound horizon of recombination. And you can do that with new relativistic particles or maybe early dark energy. But it's really not easy. So this is a paper by our host, Eleonora, showing how difficult it is to reconcile these measurements. This is another one that recently came out, highlighting how, new physics alone may not be sufficient, especially if this new physics is at early time. So it's really a fascinating problem. And I think what many of us are hoping is that, this may be the beginning of a new cosmological model. This is the dream of every physicist, find something wrong in our current understanding of physics so that we can learn something new and profound. But of course, before we do that, we really need to make sure that the tension is real and not due to some sort of systematic uncertainty. At this point, however, the systematic uncertainty would have to be in many of the measurements, right? As I've shown you before, there's a large collection of mostly independent measurements pointing to this tension. So it's really a very compelling case from an observational point of view. And I want to show you, summarize to you the contribution in time delay cosmography can give to this debate. So how does it work? The idea is very simple. Imagine that you have something that is time variable, like this fish, or a quasar, or a supernova, and the fish happens to be well aligned with the foreground deflector, or the lens of supernova quasar is well aligned with a foreground deflector, like a galaxy or a cluster. You can get multiple images. And the multiple images form at the extrema of the arrival time surface following Fermat's potential principle. And so they arrive at us with a different time. So in the case of the fish, we don't see the difference in arrival time because it's so small. But on a cosmological scale, the difference in arrival time can be days, weeks, months, in some cases even years. So it's something readily measurable. And since everything else that we measure on the sky is in the form of angles, shown in this diagram, so we have a variable source, an observer, light rays follow multiple different paths around the foreground, there's a difference in an arrival time. We can measure this difference with the clock. We know the speed of light, so we know this length. And then it's basically a matter of simple trigonometry to figure out what are the distances involved. So it's in principle a very clean and direct way to measure distances in the universe. In practice, what we do is we measure the difference in arrival time, which is proportional to something that we call the time delay distance. And like every distance in cosmology, this is proportional to the inverse of the Hubble constant. And then it weakly depends on other cosmological parameters like matter density, W, and others. But the main dependency is really on the Hubble constant. So this method is not new, of course. It was proposed in 1964, well before I was born. But for a long time, people could not do anything about this because there were no lenses. The first lenses were discovered at the end of the 70s. And so people got very excited, started to measure in time delays, and the things didn't quite match. And the problem was that you really need high cadence and high precision to do these time delays accurately. So this was solved in the 80s, 90s, and at the end of the 90s, people started to publish the first Hubble constant measurements, and clearly the errors were underestimated. And part of the problem there was that the mass models, the models that we used to describe the gravitational potential of the deflector, were based on too few data sets. And so they had to be overly simplistic and therefore could not be accurate enough. And things sort of came together at the beginning of the 2000s when we figured out how to do monitoring. We figured out that stellar kinematics is a key ingredient if you want to do this. And with Hubble and adaptive optics, we were able finally to look not just at the point source, multiple images, like multiple images of a quasar, but also at extended sources. And by 2010, we put it all together and we showed that for a simple lens, you can get down to 6-7% precision in absolute distance measurement. And remarkably, in 2014, 50th anniversary of Refsdal paper, the first multiple image supernova was discovered, and we successfully predicted its reappearance on the sky. So that was another landmark. And the first measurement from lens supernova, which is what actually Refsdal had predicted in 1964, was finally published last year. And more are coming. So this is exciting. Now, of course, this works very well in theory, but as my favorite philosopher says, in theory, there's no difference between theory and practice, but in practice, there is. So let's see how this works in practice. This was a nice example in 2014. We took an image of this cluster, then we imaged it again in November, and we saw 4 images of a supernova around this galaxy. And the interesting thing that came out of this is that we knew there was going to be another image, and this other image would reappear about 1 year after the first one. So we worked really hard to predict when the next one should appear. And we posted a paper showing a range of predictions. They should peak between the end of 2015 and the beginning of 2016, and so it did. Exactly as predicted, in December 2015, the new image appeared where we predicted it would appear and when we predicted it would appear. And also with the brightness, we predicted more or less. So that was a very nice blind, totally blind confirmation that we're doing something right, or perhaps we're not doing everything wrong. Let's put it this way. So let's skip to let's skip from history to modern time delay cosmography. So these are the key ingredients. You have to measure time delays, usually to a few percent, because you want to have a total error budget of, say, 6 or 7% per lens. You need very good astrometry. Typically, 10 milliarc seconds is what you need, because the astrometry really affects your prediction of the time delay. And so you need to use Hubble, VLA, adaptive optics. Well, now we're using JWST, as I'll show you. You need to model the lens potential. This can be done with stellar kinematics and extended sources. And one thing that had been neglected until about 2010 is you need to model the entire line of sight of the universe, because the universe is not exactly homogeneous and isotropic. There are fluctuations of mass along the line of sight. Some line of sights are overdense, some lines of sight are underdense. And so you need to account for that statistically. So to give you an idea on improvement in data quality, this was a light curve from the 80s. You would be hard-pressed to say there's a time delay here. And this is a light curve from the CosmoVerse project in the sort of mid-2000s. You can see these beautiful features here that tell you, even by eye, that the purple light curve is delayed by about 100 days with respect to the green, red, and blue. And so this gives very high precision time delays. The strong lenses, gravitational potential, this is the kind of images people had to work with in the 70s. You can barely make out that there are 4-point sources here. And this is what we finally had to work with in the mid-2000, end of 2000, where you see the 4 nice multiple image quasars, but also the host galaxy of the quasar being lensed into a ring. And one of the two is data, and the other one is a model. And you can see we can basically model these systems down to the noise level. And the other thing is, of course, measuring the lens potential here, stellar kinematics, and I'll come back to this, plays a very important role, because there's something called the mass sheet degeneracy that affects lensing-only measurements. So you need an estimator of mass that is independent of lensing. And the estimator of choice is stellar kinematics, the motions of stars in the deflector. And finally, the line of sight had been neglected prior to 2010. And we showed in 2010 that all line of sights tend to have this is kind of like the excess mass or the deficit of mass along this line of sight. 0 would be a perfectly average line of sight. Most of the universe is filled with voids, actually, because they occupy more volume. And so the average overdensity of the universe peaks slightly below 0. And then there's a tail at high masses, which is represented by groups and clusters. And for this particular object, as we inferred from the number counts along the line of sight, this line of sight was overdense. And so if you had ignored this, you would have had about a 10% error on the Hubble constant. So the other thing that we introduced around that time was blindness. So we do all our measurements blind. And the reason we do this is because we want to prevent experimental bias and make sure we don't bias ourselves to find the result that we want. And so Refsdal was a clear example of a blind experiment, because we didn't know when the new image would appear, so we predicted truly blindness, but it can be enforced in any measurement. And the way we enforce this is via software. Our analysis is fairly complicated, and we write our software in a way that it does not show us the actual mean on any posterior distribution function until the very end. So we write the paper using only blind information, and after unblinding, we give ourselves very little time, and we only usually edit, say, the abstract and the conclusion, and we may add a section or two to explain if there's something unusual. And this is nerve-wracking. The first time we did it, we said we were not going to publish a negative Hubble constant, but we would have published any positive number that would come out of this. So a contracted universe would not have been acceptable. And I've been through this a few times. It never gets easier, but we think it's important to keep it to keep us honest. Okay, so by 2020, we had reached about this conclusion that this was a measurement from the time delay cosmography. Holy cow, this work, the orange one. Okay, and then if you combine, say, this with SHOES, the measurement at that time by Adam Rees and his group, there was a very strong tension between the Planck or the dark energy surveys, BAO, and Big Bang nucleosynthesis measurements, more than 5 sigma. Okay, at that point, we went through some, let's say, some moments of reflection. Statistically, of course, this is very significant. What can we do to convince ourselves that this is really a true tension? As they say, extraordinary claims require extraordinary evidence. So the first thing we did was checking with systematics. So we embarked on a long list of systematics checks. I won't bore with all of them, but we made we wrote quite a bit of papers checking for all possible systematics. None of them really turned out to be at the level that could have explained the tension. So the next step was revisiting our assumptions. So what assumptions did we make in this measurement that could have impacted our measurement? And the key assumption turns out to be the assumptions we made about the shape of the mass density profile of the main deflector. The main deflectors are massive elliptical galaxies. And massive elliptical galaxies traditionally in the literature for the past 20 years have been described with two classes of models. One is to have some sort of mass follow light component for the stars, and then some dark matter halo, typically of an NF Navarro-Fragen White shape or something similar, or simply a power law, something where the mass density profile is of the form R to the minus something. And that something is usually around 2, but close to 2. And this is borne out by a number of observations, including X-rays, stellar dynamics, lensing-only observation, the kinematics of satellites, and also theory more or less ends up with these sort of answers. And the reason for the power law behavior is mostly, I think most people believe it's some sort of dynamical attractor where if you have a dynamical system with these properties, tends to end up being something close to what we call an isothermal sphere, R to the minus 2. Anyway, so this is kind of like the background. This is the standard of what, if you had asked any person working on elliptical galaxies, those would be the most reasonable descriptions of the mass model of an elliptical galaxy. And we showed in this paper that the Hubble constant was very stable to the two choices. If you had stars plus Navarro-Fragen White or power law, you get basically the same exact value of the Hubble constant. So what can we do next? What is the most general mass profile? What if we drop completely any assumptions on the mass density profile? So enter something called the mass sheet transformation. When you have a gravitational lensing phenomenon, if you have a surface mass density kappa x of y, that is a solution of the lensing equation and predicts your image positions very well, you can transform that with a very simple transformation. So multiply by 1 minus lambda and add lambda, which is called the mass sheet transformation. And that reproduces the same identical configuration, but it changes things like the intrinsic size and luminosity of the source and the distances involved, including the Hubble constant. Of course, some of these solutions will be unphysical because that lambda constant that you see there corresponds to a sheet of mass. And we know galaxies are not sheets of mass, right? So they're not like infinite sheets of mass. So this is a mathematical transformation. And you can sort of use that as a way to approximate all the possible families of physical models that would reproduce your lensing data. And now the only constraints on this lambda parameters or generalization of it would come from non-lensing data, okay? So that's the main concept. And so if you do that, and we did this in a 2020 paper, you end up with this sort of like decision tree. If your galaxies are described by power law and stars plus Navarro-Fragen White, so the standard description of massive elliptical galaxies, you end up with this a 2% measurement around 73, 74. Now, if you drop the assumption and you use the most general, which means you maximize the uncertainty on H naught, then your uncertainty expands to about 8, 9%, and you get 73 plus 3.3 plus or minus 6, effectively. Now, you can do something clever here, and you say, okay, massive elliptical galaxies are a fairly regular population. They follow things like the fundamental plane and other sort of things. So how about we use what we know from other lens galaxies that are much more abundant than the ones that are lensing a variable source, and try to use that information to constrain on a population level the mass density profile of elliptical galaxies. And so we did that in that paper as an illustration. And interestingly enough, the error bars shrank as we expected, but the mean value also shifted to a somewhat lower value, 67.4, which, as you may notice, is consistent with the Planck early universe probes. Now, of course, this is, at this point, there are three possible explanations of this. One is simply it's a statistical fluctuation in the sense that these measurements are all consistent with each other given the errors. So you don't know if, for example, if you had a particular, you drew a particular set of SLAX lenses that brought it one way or as opposed to the other. Or perhaps there's some difference between the SLAX and TDCOSMO lenses. As I will show, there may be some difference in the galaxy population that biases it one way or another. Or maybe this is telling you really that the mass density profile of elliptical galaxies are not power laws and stars. And so they have to be modified in a way that moves the peak of the distribution to a slightly lower number. So this is kind of where we were in 2020. So how can we make progress? How can we achieve a 1 to 2% measurement with no assumption on mass profile? And so you can do many things. So first thing you can do is better precision per system. So focusing on the systems that are time delay lenses, the ones where the source is a variable source like a quasar or supernova. You can use resolved stellar kinematics. And in the 2020 measurement, we used just an integrated aperture stellar kinematics. And that gives you much more information about how mass is distributed within the lens. You can use better external data set so that perhaps they're better matched to the TDCOSMO, the time delay lenses, and they have more information. And the other thing you can do is, of course, increase the statistics, because going back to this decision tree, you can imagine sticking to this one. If you have many more systems, the uncertainties will shrink even without assumptions or without external data sets. So we're doing all of the above, and I'll give you an update on the things we're doing now. So improving precision per system, this is the first thing. So we wrote a paper with Simon in 2021, sort of laying down a pathway to getting to do that. At that time, we had 7 lenses. This was the 2% measurement in 2020. And we showed that if you relax the mass profile assumptions and combine this with integral field spectroscopy from optical seeing limited or adaptive optics or JWST, you can get down to, say, 3% or 2%. And I think we can actually do better. I think this was a little pessimistic because we wanted to be conservative at that time. And if you increase the number of lenses, you can go to 1.5 or 2%. And in addition, if you combine this with external data sets, you can really achieve the same 1 to 2 level precision just with the addition of the external data sets. So let me show you how we're doing this. This is a ground-based measurement of the velocity dispersion and the mean velocity of a lens galaxy, lensing 4 quasars. This was published by Shajib et al. In 2023. And in this paper, we showed that with just one lens, with spatially resolved kinematics, you can get the same precision that we got with 7 lenses with integrated velocity dispersion. And so let me describe this plot a little better. This is for the same lens. So RxJ1131, this is the phone number of the lens in blue. So if you're breaking the mass sheet degeneracy with assuming a certain mass profile like a power law or composite, you get this number. If you have 7 lenses, with the MST broken, assuming a parametric mass model. This was about the 2020 results refined by the addition of another lens. This is the black number. Okay, 7 lenses are more precise than 1 lens. Then you have 7 lenses, and now you don't make the assumption of the mass profile. The precision relaxes again to this green curve. And then 1 lens with spatially resolved kinematics gives you this red curve here. Now, the interesting thing is that the red curve and the green curve have the same width, more or less. So 1 lens with spatially resolved kinematics is worth 7 lenses without spatially resolved kinematics. And we're currently working on more than 10 systems with spatially resolved kinematics from Muse and KCWI, which will shrink the uncertainties from basically the red curve back to the black curve. And I want to say this was a particularly nerve-wracking case. So we wanted to present this at the AAS last year. And so we had our unblinding ceremony, we call, where we unblind the result in front of all the co-authors. Everyone finds out what the number is on Thursday, and we submitted the paper on Friday. In fact, I remember when Adam and I were chatting about this later, I said, "You guys are crazy." We wanted to get it out by Monday. So we have a system now that works pretty well. And I think it keeps us honest, and we really get what we get. So this is now what we're doing with JWST. Now with JWST has much higher spatial resolution, which means, with respect to ground-based spectroscopy, which means we can really measure the mass density profile and also the anisotropy of the stellar orbits to much higher level of precision. So with it, going from ground-based to JWST for the same system shrinks the uncertainty from 8% to 4% to just 1 system. And this is the white light image. You see the beautiful resolution of JWST. This is a beautiful JWST spectrum. I'm not showing you the velocity dispersion because it's still blind. And you can see, you know, this is pretty amazing. Okay, the data quality is just fantastic. And 4 systems have been observed so far. 3 are scheduled, including 2 this weekend. So we'll get 1 tomorrow and 1 on Sunday. So I think these 7 systems together will be bringing us down to about, our forecast is 1.9% precision of the Hubble constant just based on these 7 systems. There's also JWST imaging that we can do. So this is a comparison of a lens observed with ACS and observed with NIRCam. Now you see with ACS, you can barely see the ring. This is what we had to work with because the resolution and the sort of contamination by the PSF is quite remarkable. But with JWST, you know, the PSF is a little funky, but you can see all these stripes here in the ring. That's real structure in the ring. And what we need to constrain the mass profile of the lens is the radial magnification. So how stretched is the arc along the radial direction. And you can see with the presence of all these little knots, you constrain that extremely well. And the other thing that happens with JWST is that lenses that were too faint and too hard to do with Hubble now become feasible because the PSF shrinks and it's more sensitive. And so this is fantastic and increases the precision of the lens model per lens. This allows us to shrink further the error budget. So there's a few systems that have been observed so far by Massimo Stiavelli's GTO data. And we think we finally cracked the PSF to the level of precision that we need to do this. So it was not easy, but I think this is now going to be appearing on arXiv soon. External data sets. What I mentioned before, when we were combining SLACs with the time delay lenses, SLACs is fairly low redshift. It's about redshift 0.2. The time delay lenses more or less peak at redshift 0.5. So this may not seem like a big difference to you, but in terms of look-back time is a few billion years. And there's some evidence that the mass density profile, so the absolute slope of the mass density profile, evolves slightly over time. And this is mostly due to the fact that there are processes like minor red dry mergers or a little bit of perhaps additional star formation in these galaxies. And these things may matter for the determination of the Hubble constant. So we want to now match the time delay lenses with a better match sample of lenses, of non-time delay lenses, that is called SL2S, which lives at the same redshift. So to do that, we got, okay, so we did two things. So sorry, wrong way. So we got better data for the SLAX lenses. This is the stellar kinematics of the SLAX lenses. And we also got new HST images of the SL2S lenses to create a better match external data set. And you can see here, these were the discovery images, and these are the new HST images. These were the discovery images and new HST images. So the improvement is quite phenomenal. And I think now we have created a much better external data set to combine with the time delay lenses. So this will be an important element. The final point is improving statistics. So we are discovering a bunch of lenses. This is a paper that came out last year with models of about 30 quadruple image quasars. This, you may remember our measurement of 2% was based on 7. Now we have 30, and there's more. So we're going to submit another proposal if you are the partner. Try to approve quasar, lens quasars. I don't know if I can say that. Maybe it's not allowed. But some of them turn out to be extraordinary. So look at this one. This is a new discovery. This is a galaxy that is lensing two sets of quasars. So there's one quadruple image quasar and one doubly image quasar, A prime and B prime. So both sets of quasars have measured time delays. And in addition to this, there's two additional sources called S3 and S4, which are multiply imaged. And so this amazing combination of constraints allow us to predict the time delay to 1% precision. So the theoretical error here, the modeling error, is very, very small. So we think from a system like this one really will be like superpower lenses for doing this kind of things. More time delays. The CosmoVerse Grail group has been fantastic. So they've been able to obtain these fantastic light curves. You can see this one combining the 2.2 meter with the VST. You see these beautiful variations in the light curve, and you can basically determine by eye the delay between the images. So there's a paper that will come out soon by Dax et al. Presenting a large collection of real time delays that have been measured for new lenses. And finally, if you have been following the literature, there's been the first Hubble constant measured from a lens supernova Refsdal. The paper came out in 2023. It took us a long time. In fact, we were joking that between the time we discovered the lens and when we published the paper, the Hubble constant actually changed because it's the present day value of the Hubble constant. So in 8 years, the change was significant, but we did it. And the interesting result, I think, is that, the Hubble constant, the preferred Hubble constant tends to be around 65, 66 from Refsdal. But, the error bars are still significantly large. This does not really allow us to tell anything about the Hubble tension. It's consistent with both the Planck and the Shoes measurement. It's just 1.5 sigma away from Shoes. But a really reassuring thing here is that this is not 32, this is not 99. And it could have been very wrong because we did this really blindly, and clusters are an extremely complicated environment to do lens models because dynamically elliptical galaxies are relaxed. Their relaxation time is shorter than the life of the universe. And so they can be described by fairly simple mass distributions, where clusters are not. Clusters are still interacting. They have lots of little clumps and lumps of matter here and there. So modeling a cluster is significantly more complicated than modeling a galaxy. And you cannot use to the same level stellar kinematics. You can do stellar kinematics of the individual galaxies in the cluster, and you can do things like X-ray for the cluster, intercluster medium, but they're not spherical systems, they're not relaxed systems, so they're not in equilibrium. So these things get much more complicated. So I think it's very reassuring. And from Refsdal, we got a decent precision, 7%, and a reasonable number in a completely blind fashion. And now two more supernova are coming out. So you might have heard of them. One is called HOPE. And HOPE is the time delay has been measured. The Hubble constant is still blind. So I don't know it. Even if I knew it, I couldn't tell you, but I don't know it. And it will be public soon, I hope. And Requiem is a 1A supernova, lens 1A supernova, that I think is going to give us another very good measurement of the Hubble constant. So finally, lens supernovas are contributing to this debate. So what to expect soon? So as far as our plans are, in 2024, we are finalizing what we call a milestone paper. This is where we combine a significantly large number of improvements so that this should represent a major step forward in the measurement of the Hubble constant from gravitational time delays. These will be the usual 7 lenses we had in the past, including spatially resolved kinematics for RxJ1131, external SLACs and SL2S dataset, several additional improvements at many levels from the modeling of the line of sight to the measurement of the surface photometry and many other little improvements. We think we're almost there. It's still blind, so I cannot tell you what the Hubble constant is, but this should be coming out this year. And the JWST NIRSPEC dataset, as I don't know if anyone here has worked with NIRSPEC IFU data. It was not for the faint of heart, but I think we finally were able to reduce it to the level where we can confidently do absorption line kinematics with high precision. And so we are churning through the data. There are 7 lenses, and the forecasted precision just from those 7 lenses is 1.9%. And then hopefully in 2025, we can combine all of this together, the 2024 milestone plus JWST plus new lenses for which we are measuring several things. Like, for example, the extraordinary system I showed you before, the one with a quadruple image quasar and a double image quasar, that's not part of the 7 lenses of the 2024 milestone, but it will be part of the 2025 milestone. And so there are many additional improvements, and it will depend exactly on some of the things that are unknown yet at this stage, but I think the forecasted precision will be in the low 1%. So this is what we're doing now. I wish I could tell you what is the Hubble constant as of today, but it's still blind, so I cannot tell you, but that's kind of like what we're going on. So my conclusion is that this greater than 5 sigma tension between early and late time measurements of the Hubble constant. And this is, of course, probably the most important problem in cosmology nowadays, because if confirmed, it would imply the discovery of physics beyond lambda CDM. And there's still some skepticism, I would say, in the community about the tension. And I think one good way to resolve this is having multiple independent methods with precision better than 2% or 1 to 2% to verify the tension and demonstrate really that the systematics are under control. One of the interesting things of time delay cosmography is that really distances are measured over gigaparsecs. So effects like Hubble bubbles or local underdensities or these sort of things play a different role than in very local measurements. So having multiple methods that are significantly different and measured over a different time scale can also help constrain those kind of, address those kind of concerns. So time delay cosmography is comparable in precision and completely independent of the local distance ladder. So that's great. We've shown that with standard assumptions, we can get 2% precision confirming the tension. Now what we're working on is to confirm and reach the same precision with no assumption of the mass density profile. And there's multiple avenues we're pursuing to do that. And I hope I will have some, maybe I'll come back here with when we have the measurement unblinded to tell you what the answer is. Thanks everyone for listening. And thanks, Eleonora, and I'm happy to take any questions.
Thank you so much. Thank you for the very great talk. Okay, do you have any questions? Wendy?
That was a beautiful talk, Tommaso. It's just,
Thank you.
having watched this from the beginning and, going back in history and where this field has come, it's just really beautiful to see that you're reaching these kinds of precisions. Anyways,
Thank you.
kudos. So I have to wonder, I mean, if everything goes as planned, and as you know, sometimes it's more difficult than the forecast would predict, but assuming you can measure Hubble constant to 1 to 2%, with what's coming in the next decade and surveys and even greater capability, suppose you have H naught, then, I mean, what are your plans? Will you learn about
Yeah,
mass distributions in galaxies? Or, what's the next step for lensing?
yeah. So there's two things that thank you, Wendy, for asking this question. So of course, this field is going to explode with Euclid, WFirst, LSST, because we're going to discover thousands of lenses, right? Supernovae, quasars, all sorts of lenses. And so there's many things you can do. First, as I said, is time delay cosmography is not only sensitive to Hubble constant, is sensitive to a number of other cosmological parameters because you do get distances as a function of redshift. And so it's very sensitive, for example, to curvature, to dark energy equation of state parameters. So you can get into those sort of measurements. Another thing that I think is interesting is that it's a high signal to noise ratio measurement in a specific line of sight. So you can start to probe things like anisotropy of the universe or fluctuations in the mass distribution in different directions or positions. So that's more like for the cosmological side. And then, of course, in this talk, I presented galaxies and clusters as a source of noise. But a lot of people are interested in learning how mass is distributed within clusters and galaxies. And I think this is the other product of this kind of work. We have published many papers, and I didn't have to go through this, about two of the highlights that were discovered from this kind of work was, for example, the fact that the mass to light ratio and therefore the stellar IMF of elliptical galaxies seem to be different than the stellar IMF in Milky Way-like galaxies, with an overabundance probably of low mass stars. Another discovery of this kind of work, I think, was the so-called, what we call the bulge halo conspiracy, the fact that it seems for some reason that massive elliptical galaxies always end up with something very close to an isothermal sphere. So there's a lot to be learned, I think, on galaxy evolution issues. And, of course, on supernova science, if you're interested in supernova, quasar science, you get things like microlensing that tells you about the properties of accretion disks. So I think really the future has a lot to offer to us.
Yeah, look forward to it.
Thanks.
Thank you. Uzena?
I'm not really working in this field, so maybe my question is stupid, but I understand that you need to model the dark matter distribution in order to get the lensing. And when you talk about resolving kinematics, then you resolve the kinematics of the baryonic matter. And then you have to couple somehow. So then you assume that dark matter follows this kind of more complex kinematics, or how you couple that to what is actually doing the lensing?
Yeah, so thanks for this is an important point. So the lensing is done by the total gravitational potential. Lensing doesn't care whether the source of the potential is baryons or dark matter or not. And stellar kinematics, the motion of the stars is also affected by the total gravitational potential. So the stars are the tracers of the potential. And so there are many ways in which you can use the motion of the tracer population to reconstruct the underlying gravitational potential. A classical simple model is Jeans modeling, where you have things like the Jeans equation that you can do in a spherical context or in axisymmetric. One of the things we're doing now, of course, with this quality of the data, we're doing axisymmetric Jeans modeling. And so there are techniques that people have been developing for decades now to infer the underlying gravitational potential for the motion of the stars within that potential. Schwarzschild methods. There are several methods that one can use.
Thank you. Erwin?
Okay, thanks for the nice talk. So at the moment, there seems to be a large spread in H0 values. So your nearest strongly lensed quasar has been revisited with spatially resolved kinematics, and you more or less get the same central value. And I haven't seen a high value for a supernovae, a lens supernovae. So no matter what the assumptions are, yeah, so that's been redone, and it's more or less 77. And then if we look at the Refsdal supernovae, then the assumptions, depending on the assumptions, it could be 64 or 66, but there's still a large spread in H0 values. And as we go on, you expect, as you analyze more systems, the errors are going to shrink, right? And then it's plausible that you can separate your H0 determinations into two groups and find an internal tension. And we've already had one paper in that direction by a Chinese group. It was marginal. It was basically sort of saying that there was a 2 sigma thing. Now, if that happens, or when that happens, where would you go looking at the assumptions? Where should we start?
Yeah, so as I said, I think that we understand the mass distribution in galaxies much better than we understand the mass distribution in clusters. So that's why initially we put most of our effort in galaxies. So I think that's sort of the easiest path. If we end up discovering a tension, and I don't think we're nearly there yet, because if you think about the Refsdal uncertainties, as I said, they are 1 sigma away from shoes. So 1.5 sigma is not something that...
but you will build up statistics. So this is something
Yeah. If it ends up that clusters and supernova systematically give different Hubble constant than quasars and galaxies, I think we'll have to think about how probably the thing I would look the most into is how we do the mass models of clusters, just because they're so complicated. But we're not nearly there, right? So this is like I prefer to talk about the present as opposed to speculate about the future.
Okay, thanks.
Yeah.
Dag?
Okay, thanks. Very interesting talk. I have 2 questions. And the first one is, it seems that your conclusion strongly depends on the anisotropy of a lens, right?
So there is a dependence on the anisotropy of the stellar orbits when you interpret. This is what Bozina was asking earlier, that when you try to go from the motion of the stars to the underlying gravitational potential, since the motion of the stars is projected and you want to know the 3-dimensional potential, you need to know something about the anisotropy of the stellar orbits. And with integrated stellar velocity dispersion, like if you have just one single aperture, you don't have any way to tell that. But the thing that spatially resolved kinematics tells us, in addition to the mass normalization, is the anisotropy of the stellar orbits. So that's why we're working so hard to get this kind of data, right? This kind of data tells us also about the anisotropy.
Okay. And the second one is, when you determine the Hubble constant, the lensed quasar and the lensed supernova, which is better, you think?
They're both great. So with 1As, the advantage is that you have the absolute magnitude of the 1As, they're standardizable candles. And so that gives you the opportunity to break the mass sheet degeneracy because you know the absolute luminosity of the source. And so that's an inherent advantage of lens supernova 1A. So if I could choose, if I could ask, the gods of astronomy to send me my favorite system, I would ask for a 1A lens by a galaxy. That would be the best solution. But we don't get to choose, so we get to work with what we have. And so they have advantages and disadvantages. And so you just have to, I think they're more or less comparable at this time. We know more lens quasars. We only know 3 lens supernovas so far that are useful for this kind of work, but they're destined to grow. So I think eventually we'll just use both.
Okay, I look forward and to see your future works.
Thanks
very much. Okay, thanks.
Thank you. Leandros?
Thank you for the nice talk. And I want to ask to what extent your results would change if there was an underlying modified gravity, for example, like a redshift-dependent Newton's constant. To what extent would your results change?
I confess I have not looked into that. So but I would be curious to find out. If you or anyone knows the answer, I'd be happy to. So far we have enough problems with our own gravity that we haven't considered modified gravities. But maybe that's something that we'll do once we have many, many lenses. I mean, I think we wrote a paper some 20 years ago trying to use lensing in dynamics to constrain, post-Newtonian sort of parameterization of generalized gravity. And it was consistent with GR within 10%, but that's not really very significant.
I see. Okay, thank you.
Thank you so much. Any other questions? No? So I think we can thank Tommaso again.
Well, thanks everyone for your patience and stay tuned.
Yeah, thank you. Bye.
Bye-bye.
Thank you for the great talk.
Thank you. Bye, everyone.